vocab that we'll talk about: continuous, maybe a new concept but fairly simple. End behavior you talked about last year. Roots and zeros you obviously know. Did you use the term multiplicity a lot last year? Okay, so you're good with those vocab, with the exception of continuous, which is new to you. So first of all, what are polynomial functions? And you dealt with them a lot last year. In general, they have this f of x equals ax to some power n plus some new coefficient, and then x to the n minus 1 power, so that the kind of the exponents continue to decrease down to some constant. We'll just call it k. So that's the look of them from an equation perspective. You did third degree, obviously lines are technically polynomial functions, right? They don't have all these twists and curves and so forth, but quadratics obviously are the next, and then you did third power polynomials, fourth power polynomials. I don't know how high you went, but once you get the concept, you could go to the highest degree, whatever high degree you wanted to go to. But polynomial functions of degree 2 or higher have smooth and continuous graphs. So smooth means they don't have any of these sharp points. So this one is an example of something that's not a polynomial function because of that right there. If something comes to a sharp point, it is not going to be a polynomial function. It's not smooth there. So like your absolute value equations, that's really the one main one you're familiar with that's got a sharp corner point. That's obviously not a polynomial function. And they also have to be continuous, which means there's no break. So this one is discontinuous right at this value of x, and so therefore it's not a continuous graph. Continuous really means you could trace your pencil along the entire thing without ever picking up your pencil. That's continuous. So this one here, this one is continuous. It just lacks being smooth at these corner points. This one here, this one's pretty smooth, but it lacks being continuous right at this little section. So what other functions have you seen that are not continuous? Think about our parent graphs. What are not continuous? Yes. Your step functions, good. Oh, they look kind of like that weird thing. Your steps. There's my quick little sketch. Pretty much anything that's not a polynomial. Yeah? Rational. Yep. So f of x equals 1 over x. So because that comes in parts. Well, I just put them in the wrong 2 quadrants, but forgive me. I'll make it negative 1 over x, so that's actually right. But that's a smooth curve. It's just not continuous because we jump over asymptotes. Something else that would... There are things that are smooth and continuous, but aren't polynomials as well. What's smooth and continuous but it's not a polynomial? Yeah, a radical. So you've got these examples that they still qualify as smooth and continuous, but they're not polynomials. Right? This is technically x to the 1/2 power. In polynomials, your exponents have to be integers. They can't be fractions. Log graphs, exponentials. I mean, there's a lot. Shoot, I shouldn't put not continuous then if we're going to include these examples. I'll say not polynomials. So I was thinking initially like non-continuous ones, but I mean pretty much all of our parent graphs that aren't polynomial functions aren't polynomial functions. Your absolute values, your logs, your exponentials. Some of them are smooth and continuous, some are not. But you have to have a degree of 2 as well. the polynomial end behavior, you guys did this last year as well. I sort of teach this maybe a little bit differently than Mrs. Ziggy, but I always tell my Algebra 2 kids, you know this. You know polynomial end behavior prior to really someone telling you what it is. Simply because you know what linears do. Right? So if you have a positive x line, that's just a line that does that, right? With a slope of 1. And a negative x line has a negative slope. So you know that this is an odd degree, right, to the first power technically. If it's positive, it starts low and ends high. If it's negative, it starts high and ends low. And your third degree polynomials, your fifth degree polynomials are going to have that same behavior. So if you're an odd degree and you have a positive leading coefficient, it starts low, ends high. And if it's a negative, with a negative slope, it starts high, ends low. And what's the even degree polynomial that you're most familiar with? Quadratics. And you've been trained since Algebra 1 to know that if it's a positive x squared, it's a parabola that opens up. So you know that it starts high and ends high. And if it's a negative quadratic, opens down, aka you don't talk about end behavior in Algebra 1, you just say, oh, it opens down. But that is the idea that it's truly getting at. Starts low and ends low. Did you ever think of it that way? Yes, some, no. So it's just a way of me to really brainwash my Algebra 2 kids to pretend like they already knew this. But you do, really. You already know these facts. So the linear facts can tell you about every odd function, and the quadratic facts that you already know can tell you about every even function. You guys saw like the different notations, like f of x approach to infinity. You did it probably with data. Is it right now? So you guys probably did, we'll do this one in the notation that you were used to. As f of x, no, as x approaches infinity, f of x approaches, so as it kind of goes, x goes towards infinity, f of x goes towards infinity. And if x was approaching negative infinity, f of x is approaching negative infinity as well. Just for that one. And you could do a different version of that for all of these. But those can get confusing, so I just like to say starts low, ends low, or starts high, ends high. We all know that odd end behavior is opposite. So if it starts low, it has to end high. If it starts high, it has to end low. Even degree polynomials have the same end behavior in both directions. They either both go up or both go down. So little patterns just to remind you of that you did from last year. So when it comes time to sketch a graph, the most important things we're interested in are zeros, and then the end behavior, and then the y-intercept just to give it the height that it deserves.